Okay. So today we're just going to be reviewing for the final exam. So I put together a few questions, a few slides, some of the answers, but we should have plenty of time for you to ask questions, things that still having trouble with, but also the rest of this week and next week. So we're only talking about what we've already talked about. We have to talk about the fact that even though we've already talked about it, all this stuff about Columbia University developing Stand, seeking additional money to develop Stand, using Stand to seek additional money, seeking to avoid people coming away without recognizing the potential for a conflict of interest due to all that seeking. So exam, it's a little fuzzy on the details last time. So I believe these are correct. Exam will be 1 week from today, May 8th, starting at 4:10, running until 7. Most likely they're going to have another exam from 7:10 to 10. So we'll have to clear out of this, not this room, but the room that the exam is in, which is IAB 405, not this one. I think it'd be pretty difficult to try to take a 3-hour exam on these desks. So they moved it to IAB 405. IAB 405, I believe, has power stations in the tables. So bring your power cords to power your laptops in addition to your laptops, so you can download all the stuff or refer to whatever need to. You can use your notes. You can use any books of the reading that you've downloaded or whatever. But one thing you should definitely do in advance is to make sure that our packages that we've used in this class, you have all of them. They are up to date with the latest versions, and they're working on your computer. Don't need to be spending a bunch of time during the exam wrestling with the fact that you changed something and now your C++ compiler is not working. So update all your stuff, test it out in advance, and then you can spend as much time as possible focusing on answering the questions rather than dealing with our issues. Questions about that? So I talked about some of the content of the exam last time. I think that's still probably pretty fair description. Questions such as those that we had in the homework, and some of the things like put up the other day to review. But basically it'll be a lot of the questions will be on stuff that we've had before with just some detail change, some twist to it. So you have to think about something a little bit different, or combine things. Probably a good thing to ask in final exam questions is go back to some of the things that we did earlier in the semester, but now that we've gone through the whole semester, utilize some of the techniques that we talked about or learned about in the middle or toward the end of the semester on earlier problems that we didn't have the tools to go into as much depth or as much sophistication at the time, even though we were trying to build up to be able to use those tools as fast as we could. But it's pretty clear that there's no way we could have gone any faster overall, covered plenty of content to put on an exam. But if we'd gone any slower over the course of the semester, then we wouldn't have had an opportunity to do a homework on writing your own programs in the Stan language. We were just barely able to squeeze that in on the pace that we were going at, and I think that is important. You certainly could design a class that was like only RStan ARM or only RStan ARM and BRMS, but I think that doesn't really capture the scope of the things that you can do with Stan if you can write or modify programs in the Stan language. But also you really have to think about how to write things in the Stan language in order to really understand what RStan ARM and BRMS are doing. I mean, those are very convenient, particularly in the case of BRMS. You can estimate tons of models, but to get an appreciation for all the things that you have to think about when putting together a model, it's helpful to push yourself to do that yourself. Particularly with RStan ARM and the priors and stuff, it allows you to kind of skip over thinking about a lot of things that when you write your own model, it forces you to think about all the little details that go into a model, and not only little details of how to write down the model, but how to go about sampling from the implied posterior distribution with a reasonable amount of efficiency. And so there's so many things going on behind the scenes with RStan ARM and to a similar extent with BRMS that are trying to do that those small details well for you, but they don't necessarily are going to work in all situations, and certainly don't cover all possible models that you could write in the Stan language, and models that you could write in Stan language and be very successful in efficiently drawing from the posterior distribution of them. So they're good learning tools because you definitely don't want, as you're going along, don't want to get too caught up on the small details like is it running into its maximum tree depth or things like that, when you're just trying to learn like what is draws from the posterior distribution, how do they differ from independent draws, what do we do with them, like how can we use all this things with the Bayesian machinery to do model comparison or projection pursuits, all those things. Those are more conceptual ideas, and those are important to learn too. But when doing this in practice, you really do have to think about a lot of those little details, and in doing things the right way, following the Bayesian workflow forces you to think through all those. Okay, so first question, particular scene from Dumb and Dumber manages to do a pretty good job of illustrating the process of Bayesian inference, not necessarily estimating something precisely in Stan, but the overall idea of updating beliefs, learning, etc., in a pretty simple setting. So how would you map on what is happening in this scene to the concepts or the process of Bayesian inference, the way in which it utilizes probability? Yes.
Isn't he updating that the other way around? I had something.
He was updating the other way around?
Yeah. He started from 1 to 100, then he had 1 million happier.
Right. So there's definitely an updating of beliefs. It probably would have been happier still if he'd gotten 1 in 100 than 1 in a million. But that's why I said, how would you describe his loss function for, or utility function for this particular, associated with this posterior? Or you can, loss function, utility function, they're just multiplied by -1. So you can, so utility function is all in the Bayesian context, it's going to be for some decision or some action that you would take as a result of having updated beliefs about the unknowns.
But is his function that he's gonna get what's her name?
Mary.
That he's gonna get with Mary, or is it that he has a chance? What is
Right. Well, so with these loss functions, utility functions, you always are sort of taking the expectation over the things that you don't know. And so if that posterior distribution has, let's say, an expectation of 1 in a million, or you take that posterior distribution, multiply it by the loss function, integrate it up, he seems to be pretty happy about that. And so the expected utility, even on something that is stated to be as low a probability as 1 in a million, still makes him happy in expectation.
what's the happiness?
Well, utility, yeah,
Okay.
right.
So it seems, I mean, in that way, like, I guess his loss function, like, he would be unhappy if it was 0 out of a million.
Yeah.
But with 1 out of a million, he's
Right. So presumably would have been happier with 1 out of 100, although he is either dumb or dumber, so it's possible he's just got his numbers. What sense of, or what view of probability is at issue here? Definition of probability, perspective of probability. Andres?
Subjective.
Definitely subjective
The
probability.
way of thinking of that scenario is imagine it happening a lot
So
of
you
times.
can watch Dumb and Dumber over and over and over again. Doesn't change. But, even if it did change, that's not the sense of probability. Groundhog Day arguably comes closest to representing frequentist view of probability, but even still, not exactly, because he's changing what he does each day as a result of what happened in the previous iterations of Groundhog Day. So it's not as if we have independent trials or anything like that that exactly fits into. But this clearly relies on the subjective view of probability, and it's something that is, well understood what people mean when they're talking about different subjective probabilities, the process of, updating. And it's something, people who are watching that movie, it seems entirely intuitive to them. So I think, the same principles of, updating beliefs, having, subjective probability about other things, should be, equally intuitive, equally explainable to people who, watch movies rather than study statistics. Now, the details of like drawing from a posterior distribution with Hamiltonian Monte Carlo in order to sort of, more precisely estimate these expectations rather than just say, okay, well, it's about 1 in a million. Obviously, that takes a lot of specialized training, hardware, those sort of things. But the ideas of it, if you look and you I think probably the first time, that you would see one of these movies or whatever, you just sort of, before you learn about statistics and probability, frequentism and stuff like that in graduate school, you would just say, well, that's kind of the way probability just kind of is, and the way people utilize probability for those sorts of things. But, when you get to grad school or, once, the past 100 years or whatever, they tend to start off almost invariably in, this is how probability is defined. It's the frequency of it. It's the proportion of times that something happens if you do, repeated experiments over and over and over again. So redefining the ideas of probability that, you grew up with. And so in that sense, it's sort of a departure, even though, once you take sort of the mandatory classes and you learn the way of, probability and you have some experience doing like OLS and logit models or whatever, and then, a class like this comes along and we're trying to get back to the more intuitive, certainly subjective. Did you just see that for the first time? Okay. 1 in a million. No, but Jim Carrey and that woman, Holly, I can't remember her last name, actually were married for like a year after that, which is one of the great ironies in history. Not for very long, but yeah, they did get married. Anyway, what was I saying? Yeah, so yeah, really going back to the way in which people deal with probability informally, and then adding a whole lot of formalism, on top of it, instead of saying, okay, like 1 in a million, maybe it's a beta distribution that has an expectation of 1 in a million, and it has, uncertainty around that, integrates to 1. So even though, we talk about a lot of, complicated concepts and nuance and, estimating things and, leave one out processality, all these things, we're, piling it on to what hopefully is an intuitive way of talking about probability, understanding probability, and not only more intuitive and easier to understand than the sort of definition of probability used by frequentists, which doesn't seem to have a whole lot of connection to what people are doing in the real world or what researchers are doing when they're trying to research something, particularly in the social sciences. But don't lose sight of the fact that it's intended to be the intuitive way of.
So I got confused because you were asking about the loss function. So in my head, that's just what you have a set of probabilities and you have action that you want to take in.
Right.
After edge order that.
Yeah. So.
But it didn't seem like I could extract the loss function.
Right. Okay. So the way to think about this, okay, there's a decision or a hypothetical decision that they could get married. And so there's, one utility if they don't, which has, let's say 999,999 out of a million. You get, whatever baseline level of utility. Again, with utility doesn't really have natural units. So you can just define the baseline case as like utility of 1 or something like that. And then there's another decision that could be made. They could get married, and then it has a different utility to it. So if you're just thinking about a decision space that has 2 possibilities, and that has a 1 in a million probability attached to it. So how will we take the expected utility?
Okay, I see. And would you want it for one to be higher than the other, or for it to be fair?
Well, life's not fair. And you know, it turns out in the movie they don't. But anyway, yeah. I mean, you would want to, you know, one, have coherent set of beliefs, so update them in light of whatever information they have available. But then, you know, taking the decision to maximize expected utility, insofar as that's something that you can control, which involving like 2 people getting married, you can't really do that unilaterally in the United States. But you know, in terms of using these ideas, okay, you know, update your beliefs, know what your loss function is, and then insofar as you can affect these things even probabilistically by making one decision or the other, doing so in a way to maximize utility. And so just to make it explicit, let's say you have utility 1, they don't get married, so you multiply that by the probability, almost guaranteed, plus 1 in a million chance of getting married, multiplied by whatever the utility of that is, and that is expected utility. And apparently Lloyd, you know, weighted so highly utility of marrying Mary that even, you know, a 1 in a million chance resulted in a non-negligible expected utility. So you can think about this same way you would, you know, like a lottery ticket. You get sort of baseline level of utility if you don't win the lottery, which is almost guaranteed to happen. And then you have something on the order of, you know, 1 in 10 million, 1 in 100 million, something like that, of winning the lottery, which could be like, you know, $50 million or something like that, have to work out whether the expected utility of buying a lottery ticket is, you know, worthwhile. In most cases, it is not.
I swear this is the last question. Isn't examples like this one of the reasons some people are suspicious about with subjective probabilities?
Yeah. Yeah. I think, you know, it's certainly the case that, you know, you know, Lloyd says, you know, 1 in, there's no additional data. They really just were saying their respective prior expectations, you know, 1 in a million or 1 in 100. I mean, there had been a lot of data throughout. This was toward the end of the movie, for those of you who have not seen it before. So there was a lot of things that led up to that scene. But anyway, so yeah, I think that illustrates the fact that people can have different probabilities, you know, over the same event, same data. But I don't know anyone who would, you know, really say that there's an alternative to using subjective probability in a situation like this. Like, I don't know how Fisher, or one of the people that continues to promote the idea of frequentist inference today, would apply frequentist perspective probability to something like that, or the Super Bowl, or, you know, whatever it may be. So I don't think, yeah, typical sort of Bayesian response is just, you know, all this sort of stuff is like inevitable. And I think from a frequentist perspective, you have to just say like, that's not something that we can, or frequentists can really say anything about. If there's no prospects for just like doing many independent trials over and over again to ascertain what these probabilities are. And then toward the end of that scene, how did the beliefs get updated again? Already married. So I think that resulted in even lower probability.
That's for sure.
It took place in Utah. So.
She already knew he had a husband before she said one.
Right.
But yeah, he said that.
A lot of stuff going on. Questions about that? Questions about sort of subjective probability, Bayesian view of probability in general, not necessarily connected to dumb and dumb. So second question had several parts, but all had to do with different distribution known as the product normal, which is defined as the distribution of the product of k independent normal random variables, each with the expectation of 0, although they can have a different standard deviation. So just to simplify it down, as you think of the case of two standard normal, just keep it simple, standard normal random variables multiplied together, not the densities multiplied together, but actually take the function realizations, multiply those together, the product is going to have a different distribution. And this distribution is known as product normal. And we can write using the definition on Wikipedia or whatever, the PDF of this in Stan. So this one is going to be a little bit different for reasons that hopefully will become clear. But more like we do in R, the first argument is allowed to be a vector, and this particular function is a bit rare for Stan functions. It's actually going to return a vector of the same size that is going to have the PDF value at each of these independent realizations from this product normal distribution. Pass in scalars for the standard deviations of the constituent random variables. Those will also go into the PDF of X. So we get N, which is the number of rows of X, the number of observations that we're dealing with. We want to make an out vector of the same size. In the PDF, it involves the product of the two standard deviations of the underlying one. So we multiply that together, loop from the first observation to the last one, and except at one point, the PDF can be written as this Bessel function with order 0, evaluated at the absolute value of X divided by sigma, which again is the product of these two things. And then outside the Bessel function in the denominator, we have pi the number associated with the circle, and again, scaled up or down, whatever it may be by sigma. However, if x is exactly 0, there's the asymptote to the function, and the PDF or the density function goes to infinity as the value of x approaches 0. Get through that loop, return the out vector. Robert.
Sorry, what is the input vector x here?
So the input vector is going to be realizations of the random variable x, and x is the product, defined as the distribution of the product of a bunch of independent normals, each with mean 0, multiplied together. Okay. So in the case of, let's say k equal 2, so 2 multiplied together, each of your n observations on x, you're thinking of being generated according to a stochastic process where each of those n observations had sort of 2 independent normal distributions associated with them that you don't see, but you see their product multiplied together. And you're now trying to describe the distribution of x, the product of k things. Okay. So we haven't done, I think before this, what's the distribution of product, but that's really one of the main sort of things in probability, in addition to saying like, okay, what's the distribution if we transform it this way or that? But a very standard thing is like, what is the distribution of 2 independent normal random variables summed together? Also happens to be normal. Difference in this case, same as the sum. What is the distribution of the ratio of 2 standard normal independent random variables? Distribution of the ratio of standard normals, standard quotient. So we get lots more distributions by saying, what's the sum of a bunch of variables? What's the product of a bunch of variables? What's the ratio of 2 independent variables? What if they're not independent? What if they're correlated? Those things like that lead to this proliferation of distributions, presumably one of which will be appropriate in any given scientific research situation or other situation in which you want to apply Bayesian. So this is one of them. Please.
So for which kind of situation would this distribution be helpful?
Well, I think it's because of the shape of it, it's potentially a very useful prior distribution for regression coefficients. So we'll see that in a second. But for some sort of data generating process, if you sort of are in a situation in which you don't see the underlying variables, but you think there's like an additive process where stuff gets added, or a multiplicative process where stuff gets multiplied, and you just sort of see the end result variable, then it's good to be able to work with distributions like these that go through that, the algebra when applying some operation to the underlying variables that you don't see, and being able to derive a distribution for what you might see.
If I'm using this one, it's then me saying, oh, like I'm also assuming that in that process of the generation that I might not see, those 2, or like however many random number variables they have expectations.
Yes, and they're multiplied together.
Yeah.
And so it's not too surprising that the product is also going to have an expectation of 0. But other things, I don't know if we explicitly talked about it, but let's say you have 2 random normal variables that are independent. They have mu1 and mu2. The sum of them is going to be normal, and the expectation of the sum is mu1 plus mu2. The variance is more complicated. But anyway, yes, Robert.
Possibly another question. What are we actually getting out of this function? What exactly is going on?
So this is like an R function. You can put in a vector of 10 things, and you get back a vector of 10 density evaluations at those random variables.
Okay. At that exact point.
Yes. Right. And so if you think of this vector as being like infinitely long, then we're going to be able to plot this and we can see the whole shape of this distribution. But before we do that, ask some more basic questions. So what is the sample space of X, the product? No. So sigma just sort of tells you the underlying standard deviation of the constituent terms that are multiplied together. But you know, even a normal distribution with a standard deviation of like 1, you could see a realization of that that's like 1.5, closer to 2, etc.
All the numbers but 0.
All real numbers, but 0 is included or excluded? Why would 0 be excluded? Well, I can multiply 2 or k things, and if any one of them is 0, then the product is 0. Then all real numbers, yeah. So 0 is included. All real numbers, you know, you can multiply things, and you know, depending on the mix of positive and negative, and whether you have an odd or even number, you know, the product could either be positive or negative. So yes, all real numbers, but we'll see in a second that there's going to be a lot of concentration around 0. So how would we show numerically using R that the previous function is in fact a valid probability density function? Not so much that it is the probability density function when you multiply k independent random normals with expectation 0 together. You have to do like analytic work to show that. But this function on the previous slide, it is a valid PDF of something. Happens to be the PDF for the product of k normals with expectation 0. But how would we show that this is indeed valid? It satisfies the requirements for a PDF. What are requirements for a valid PDF? Right.
Integrates to 1.
Integrates to 1.
The whole sample space.
Over the whole sample space, which we said is the whole real numbers. Yeah.
In R realistically integrate very low number to a very high number.
Yeah, that's going to be fine numerically. Okay. But there's additional criteria PDF has to meet besides integrating to 1 over the entire sample space.
Whether you have any value of real number space squared or equal to 0.
Right. Well, the density has to be 0. Since this is a continuous random variable, the probability of any one point we're letting approach 0. But the density function has to be non-negative if you evaluate it anywhere in the sample space, which is all real numbers. There's another thing about things being you know, mutually exclusive, but in the case of a random variable defined, univariate random variable defined over the whole real number line, that is sort of satisfied automatically. So the fact that this, well, 1, it has to be a function. That is implied by the fact that the Bessel function is a function. Moreover, it's a non-negative function. So if sigma 1 and sigma 2 are both positive, pi is positive, you just basically have division of a whole lot of positive numbers going on here. So it's going to satisfy the positivity requirement, and then you can use the integrate function in R to numerically integrate this function for given values of sigma 1, sigma 2 from, you know, what R represents as negative infinity to positive infinity, and see that that numerical integral is sort of within numerical tolerance of 1, which it is in this case, if you were to do that. So returning to this issue, if you evaluate the function at x equals 0, you're going to get infinity. You can verify this in R. It's not just a stand thing, that if you evaluate the Bessel K function in R at 0 and 0, order 0, and then the value 0, you'll get back positive infinity. So if the density is infinite at 0, how can this be reconciled with your answer question 2, where if you went through this process, we would find that the whole thing integrates to 1. But
I guess for the density at like any single point, like there's no density on the probability.
right, it has no width.
It has no.
So any individual point in the sample space can have a density of 0. Any interval, subinterval of the sample space, not just the isolated point, but subinterval, it can have density that pokes up above 1, as long as the whole thing integrates to 1 over the entire sample space. So you will often see, and depending on like your standard deviation, you can just see this from a normal distribution, that for some parts of the sample space, the density pokes up above 1. For other parts of the sample space, it's well below 1. If you sort of aggregate that area up, it comes out to exactly 1. But there's plenty of distributions that have spikes to infinity at some point in the sample space for the density function. Example of which is a beta distribution. If you have both shape parameters less than 1, it has this U-shaped shape to its density function. That's a little bit weird, but it's actually, the density function is going to infinity as you go, either approaching 0 or 1. Now, it's more common with Bayesian analysis to use beta function where both shape parameters are greater than 1, in which case you have this upside down U-shaped, and the density function is finite everywhere, and it has a mode. So when thinking about like priors and stuff like that involving a beta distribution, usually you want to put yourself in a situation where the mode exists, so you can think about, okay, what's the most likely value for this thing, and that along with maybe what you believe the median is or the mean, something like that, to pin down the shape parameters that you want to use for your beta prior. So we saw that a number of times over the course of the semester, and like the paper from Humphreys and Jacobs could have done a better job, I think, of reaching out to the more qualitative research scholar community by saying, it's not really that hard to choose hyperparameter values for a beta distribution if you think about, what's the most likely value, what's the over/under, what do you expect it to be, those sorts of things, and then map it on to these like shape parameters of the beta distribution that are usually used in its definition. Other questions about 2 or 3, Becca?
So I still don't understand how it can be valid and integrate to 1 if we include 0 in sample space. That if the value is exactly equal to 0, it is.
Right. So with integration, we're not summing points. We're summing or accumulating area. So if you think about this point-wise, then it's not going to make sense for a density function to ever be above 1, because if that point causes the density to go over 1, then it's going to sum up to something that's greater than 1. But that's really the fundamental difference between probability mass functions that are defined on a discrete sample space, in which we really are summing point probabilities, and probability density functions that are defined over a continuous space in which we don't have any real point-wise concepts, because the probability of any one point is approaching 0 in such a way that the integral of the density function over all those points integrates to 1. So you have sort of the probability approaching 0 and the the density at some of them going to infinity, offsetting in such a way that the area is the 1.
But if it's exactly 0, then
Right, but the probability of it being exactly 0 is exactly 0. So
then why is 0 included in the possibilities for x? Okay.
well, the probability of it being 1 is also 0, or any number like 1.137, also going to have a probability of 0, even though the density is finite in all those places. So you're going to have a probability of 0 at any particular point, irrespective of what the density function is. But the density function is basically normalized in such a way. That's why we're dividing by pi and dividing by sigma and all that stuff in order to make the integral be exactly 1. And, up to the precision that your computer can do numerical integrals, it's extraordinarily close to 1. Yeah, but I mean that, and this is intended to illustrate the sort of less intuitive aspects of probability for continuous random variables. And you have to deal with integration rather than you have to do like derivatives to get from the CDF to the PDF and stuff like that, rather than doing the more simple things that we can do with discrete random variables that basically just involves multiplication, summation, the sort of stuff we did with bowling, Poisson, kinds of things like that. All right. Questions about that? Okay, so use the curve function to compare this. How would you compare it with univariate normal? So code to do something like that. So here it is. We just call our function, let it plot. I did 1,001 points. You can see there's actually a little bit of a gap there. The function didn't get evaluated at exactly 0, and so it didn't go all the way up to infinity. That would have been hard to read, but you can see it's sort of rapidly going up as you get closer and closer to 0, as compared to, let's say, standard normal distribution that has sigma of 1 as well. It's if you're familiar with this, there's a small probability of it being less than -2, greater than +2, but the product normal distribution is not really the resolution that you can see, but it's actually a little bit above the red line, even going out to sort of far-ish values. It's symmetric, so the same on the negative side as on the positive side. So you can basically say, well, all this area, from like 1 to 2 or whatever, where there's less density for the product normal distribution than for the standard normal distribution, has to go somewhere, because both the black curve and the red curve are going to be integrating to 1. So where does it go? Well, there's a concentration of it near 0, obviously, but there's also heavier tails with the product normal distribution, and that's one reason why it, among other distributions, might be a good candidate for a distribution on regression coefficients, particularly if you have a lot of predictors. You're basically saying there's a high probability that it's very near 0, but there's a non-negligible probability that that coefficient is very far from 0 because of the heavy tails. It's a little bit easier to see if you make a bigger plot and one that has not so much width, or doesn't have twice as much width as it has height. But trust me, if you plot this yourself, you can see that the tails of a product normal distribution are heavier than those of a standard normal distribution. So in addition to concentration 0, you're getting more probability of something like 5 than you would under a standard normal. Andres.
Get stream arguments.
Yeah, don't worry about that. That's going to be in the next version of RStan. You're going to have to pass that in order to see the messages that come back. So I didn't put any messages in this one. It's kind of moved. But anyway, for your version of RStan, you wouldn't have to specify that.
I was following it.
Yeah. So,
Did you define the x default?
no. So the curve function basically passes like a whole bunch of values of x to it, so it looks as if it's being plotted smooth. It's just the resolution of it is less than a pixel.
And for genome, you just don't specify how many values it should have. It's just
Yeah. So actually, in the original one, I specified 1001, and if you do add equal true, it just applies the same settings, different function on the same plot. Okay. So we talked a little bit, talked a little bit about using it for regression coefficients. So what would be the posterior mode if you use this as your prior and you conditioned on some data like in diamonds or whatever?
Doesn't that depend on the data that you use to condition on? Because if the product is 0, but it depends on
The entire distribution, certainly posterior distribution, conditions on the data. Indeed, that's the essence of the Bayesian approach. So you condition on the data that you have, nothing else. However, in this case, is the mode affected of the parameters, coefficients, regression coefficients affected by the data.
Given our previous discussion, it's not defined.
It's defined. So, yes, it's infinite here, but the mode is simply defined as the value of x with the highest density. So the mode is defined to be 0, even though the density is not finite there. But if this is my prior and then I condition on the data, what happens to the posterior mode?
it's still be 0 because if you
Irrespective of what the likelihood is
if you multiply
at 0. Right. So provided that the likelihood is well defined at 0, which it should be if you're using it as the likelihood function, then yes, the product of the prior and the likelihood is going to result. Posterior mode still going to be infinite at 0. However, that just speaks to the lack of relevance of the posterior mode. So I think the mode is definitely a useful concept. It's very useful for specifying priors because you can just sort of think, okay, what do you think is the most likely value? But once you've conditioned on the data, the mode is kind of a red herring. So in this particular case, it's always going to be 0 irrespective of what the data is. But the posterior distribution as a whole is going to change. It's going to depend on what the data are. So posterior median, not going to be 0. Posterior mean, not going to be 0. The variance tends to be finite, all these sorts of things. So really what happens, yes, you get still a mode at 0, but it's so skinny that it's really not contributing very much at all to other things like the expectation or whatever that's also defined as the integral over this space of, you know, X multiplied by the posterior density, or whatever it may be. So you condition on data, like the Diamond's data set, particularly if you have a lot of data, and you look and you may see, well, you know, the posterior mean, the posterior median is like, you know, 1.8, something like that. But the posterior mean, posterior median are a better description of this, you know, center of the distribution, defined in different ways, but than the mode is, particularly in more complicated models. In addition, the mode depends on how you do transformations and stuff like that. So you might think, okay, if I have this, and then, you know, there's some posterior mode for this parameterization, and I like do the log or something of this parameter, then, you know, the mode is going to stay the same, or the mode is going to change in some predictable way depending on the transformation. That's not true. So the mode is fragile in a sense that it depends in non-obvious ways on what the parameterization you use is. Whereas like the posterior mean or whatever, it does respond in a entirely predictable way when you do a transformation, as long as you do the transformation right with the Jacobians and stuff like that to adjust your density, the expectation is going to come out the same. So the expectation is not sensitive to parameterizations, whereas the mode is. So if you do the Diamond's thing, get this, do like a summary, you can see, you know, where the 75th percentile is, where the 25th percentile is. There's actually a function in RST-ARM called posterior interval, where you can get out any size credible interval that you want, and you may very well find for a lot of these coefficients in this example that it does not include 0. And so there's sort of, you know, greater than 50% chance, greater than 80% chance or whatever that one of these coefficients is positive, even though the most likely value for each of those coefficients is going to be 0 because of the nature of this prior. Rishika. Just because there's like 50,000 and it takes forever to fit the whole thing. Still takes pretty long to just do 10,000. You might want to do 1,000. But in a situation like this, you can estimate all the coefficients very precisely because the Diamond prices are pretty predictable. Okay. Does it underfit, overfit? We talked about this before. You can do graphs, but, you know, one of the interesting ways of, you know, doing this just with sort of numbers is to get the posterior predictive distribution, get the interquartile range of each of the columns, use that as your lower and upper bound, and calculate up the proportion of times that the predictive observation falls within is greater than the lower bound, less than the upper bound. And if you construct a 50% interval, then you should expect 50% of the observations that you condition on to fall inside those intervals. Now, it's not going to be exactly, could be a little bit more, could be a little bit less. In this case, I think you'll probably find that it comes out reasonably well. And even if you do this on the testing data, you'll find should be pretty similar results. And so the sort of pretty common thing that you hear, particularly from the more machine learning literature, you always have to split up your data into training and testing, and only use the testing part of the data to evaluate the compare different models. And that's not entirely true. There's a seed of truth in that. But even if you don't have like tons of excess observations, even if you have to use all the observations that you have to condition on in order to get the posterior distribution, you ought to be able to tell just from the so-called training data, even if there is no testing data, whether you're overfitting or not. And so, yeah, it may happen a little bit, but you should know. And also all the sort of leave one out stuff to tell you, you know, what would be the prediction if we were to, you know, rerun this, excluding the 7th observation and then getting the posterior distribution and then predicting the outcome for the 7th observation conditional on, you know, everybody else, is another way of combating this sort of tendency to slightly overfit a little bit when you condition on your actual data. Projection pursuit approach. So this was the idea that we talked about, you know, not so much for this diamonds example where we really only have a handful of predictors, but in a situation in which you have tons of potential predictors, you don't really know which are relevant ones, but you want a relatively simple model that predicts future data as well. You can go through this process of estimating or drawing from the posterior distribution, inclusive of like all or most or, you know, whatever your predictions, lots of interactions, stuff like that as well, using priors like the horseshoe prior, product normal prior, things like that that have a significant concentration of near zero. So if you don't have a whole lot of information in the data, the posterior distribution of those coefficients will also be, you know, tend to be near zero. But if it does have a really strong effect, then the prior is not so strong. It allows the posterior distribution to show up in that. And then, you know, after estimating that whole posterior distribution, you can use the functions in the proj-pred package to try to find a model with a fewer number of predictors that is still expected to predict future data almost as well as the original model. Again, the metric for evaluating whether it predicts future data better or poorly is going to have to do with this leave one out stuff, using Pareto smooth importance sampling to, you know, do corrections of that, you know, truncating the weights, all the same ideas that we talked about with Lou, you know, being applied to this situation of trying to find, okay, could we use like 5 predictors and get about the same expected value for the density of future data? And if so, you know, what's the best model that only has 5 predictors coming out? And you can use cross-validation and a variety of plots and stuff like that in the proj-pred package to get at those sorts of things. Rashika.
I think about like when you do that for snow packing, you get a big how do you like which variables come?
Good question. So if we go back to those things, those of you who are in data mining in the fall, the variable importance plot is kind of a misnomer. Correct description of that thing would be what variables are split on the most number of times in this sort of random bootstrapping tree splitting thing. So to sort of condense that to importance is a little bit. So by definition, if you have like dummy variables, they're not going to be split on more than once. So, you know, it doesn't mean your race is like not important or your gender or, you know, whatever. So continuous variables have a bit of an advantage in the who can be the most important variable because you can split on them arbitrarily large number of times. So anyway, we're talking about what variable is split on the most. Now, with the Bayesian thing, or, you know, with any Bayesian thing, not just this, we really want to define importance in more substantive terms. And so in the random forest thing, importance and number of times you split is really more associated with like how nonlinear the relationship between a predictor and outcome is. So if you want to say, okay, this variable is more important than the other, you have to define really what you mean by important. But a step in that direction is, okay, you know, what variables predictors contribute the most variation to the outcome. And there's a like very easy and essentially foolproof way of doing that from a Bayesian perspective, which is obtain the posterior predictive distribution, based on the data that you conditioned on, and then ask, okay, what if everyone had the same income? Get a new posterior, leave everything the same except income, fix everybody's income to the average or the median, whatever, it doesn't really matter. Now let's compare the variation in the outcome, like voting behavior or whatever, in those two scenarios. So if your idea of importance is like what contributes the most variation to a variable, we can answer that very directly by saying, okay, here's how much variation there was sort of naturally, and here's how much variation our model tells us there would be in the outcome if everyone was the same age, or if everyone had the same income, making the variable of interest a constant across observations, and then seeing how much the variance in the predictions decreases. And so utilizing what the model tells you in terms of the posterior predictive distribution, not only easier to interpret, you can directly answer the questions that you want to ask, and it should be very transparent what you're doing. And it's, except in like linear models, Gaussian, no link function, etc., it's almost essential, because the relationship between the outcome and the predictor is being like muddled, not muddled, but not distorted. I don't know what the word is, but with the link function and the interactions and all this, you can't just like look at the coefficient and understand the relationship between the variable and how it predicts under your model. But using posterior prediction and graphs, it ought to be very clear what that relationship is, even though that relationship will not be a straight line. So yeah, it's always possible to do, and it's almost always the easiest thing to do is to compare factual and counterfactual posterior predictive scenarios. All right, so we can do that. So just quickly go through this. For the more expanded version of this open policing sort of paper, it had some missingness. So what are the definitions of IMCAR, MAR, IMNAR, INMAR, etc.?
So we're missing completely at random.
And what does that mean?
Which is that you're assuming that the variable, the missingness is just no relation.
Yeah, it doesn't depend on any of the variables, only depends on parameters. So basically, like, you flip a weighted coin, that determines whether you're observed or not observed on the variable. Okay, that's IMCAR, missing completely at random, which is not missing conditionally at random. So these?
Yeah, that's basically MAR and AR. So missing at random would be missing conditionally at random, because it's missing
Conditional on what?
Conditional on some other for instance, covariates.
Yes, but in particular, the observed values of the covariates. The important thing about missing at random is that the probability of missing this does not depend on the true values of the things that we're missing. It only depends on values that are observed. So if like age is fully observed, and whether you're missing on education or income or something like that, only depends on your age and possibly some parameters or whatever, then say that's missing at random. But if the probability of being missing on income, education, race, things like that actually depends on the underlying value that's missing, So, rich people are less likely to report what their income is than poor people, stuff like that. Then the data generating process is missing not at random or not missing at random, which means the same thing. So they have data from like 20 states. They don't have adequate data from like 30 states. Based on the description in that paper, do you think that missing this, which category would that fall into? But
I guess it's not missing at random because it's like certain states and they might have reasons why they don't collect that data that are not like your services.
yeah, so that should always be your suspicion. If whatever state won't give you data, particularly if the state actually like collected it, but they won't give it to you, the researcher, always have to be suspicious that there's something in the data that they don't want researchers to see, and so that would suggest sort of the behavior of the police is like worse than your marginal expectation of police in the United States. Now, if you looked at the states, it wasn't exactly what I would have thought. So you would sort of guess that like the southern states or whatever would be less likely to report their data on like different police stopping by race and stuff. It didn't exactly come out that way. But that doesn't mean it's not that doesn't mean it's missing completely at random. So you got to think about those processes. But at least in this situation, it's if the state is like, yeah, we didn't have the money in the budget to collect what you want, or something like that, then that process might be a little bit more benign than if a state was like, yeah, we'll give you the police stopping data, but only for white people. And you have to ask yourself, why would they do that? Anyway, so section 2.3 of the paper talks about various corrections to the data, most prominent of which was Texas, which actually did provide the data, but in looking at it, it seemed as if there were a lot of situations in which the police officer wrote down the race of the person as being white, even though the last name of the person would suggest that they were Hispanic. And they did like some stuff with the big list of names and stuff like that to and the census data and stuff like that to recode basically people who have names like Hernandez or whatever like that. If they were coded as white, then they would be recoded as Hispanic in the data. So what did you think about that? What sort of issues with that approach there? So basically not so much missing data here, but possibly misclassified data. Yes.
I have a question more than an answer. So
Okay.
I assume that if there's like, from a perspective of the police officer, if they're stopping somebody and we're trying to measure basically like racial bias, if they assume that they're right, even when they're not, would it perhaps be like isn't that a good thing? Wouldn't you just take their measure of somebody being white even though they aren't, because that was their perspective on this person's race, and so then you're measuring bias in the wrong way?
Yeah, it's worth thinking about. So, certainly if the person stopping you sort of legitimately perceives the person to be white, even though like their DNA or whatever may suggest that they're, parents or their grandparents or whatever came from Mexico, then maybe the police officer treats that person, or in terms of searching their car or whatever, differently than what they would have if the police officer had actually recognized the person with the pen. That's one way of looking at it. Another way of looking at it, well, maybe the police officer knows perfectly well that someone whose last name is Hernandez is probably, like, if you ask them, they would self-identify as Hispanic or Latino or something like that. But they just sort of write down white because they don't want it to look like, they're stopping people disproportionately. So it could go either way. What did you think about their way of, the author's way of correcting for this possible misclassification? You see this technique being used a lot these days because, like, we pretty much know in each county or whatever from the census data, one, what is the marginal proportion of people in this race and that race, and also for a lot of states with, like, the birth certificate or something like that, we have the frequency with which someone with the last name of Hernandez self-identifies as Hispanic. I think it's going to be like 94% of the time or something like that. So these are used a lot in some of these cases in which we don't exactly know, to the extent we ever know, what someone's case is for voting cases and stuff like that. But what do you think about this correction? Or is it an incorrection? What would you want to watch out for?
So, part of the problem is once you've corrected it, then it's no longer missing, and therefore any of the reasons why it was missing have also been
Yeah. So there are probably some situations in which the police officer also forgot to write it down. But apparently those are not that many because it's part of their law or regulations.
Or it's no longer, once it's corrected for you, you've thrown out sort of the information about why you corrected it, or that it was corrected at all.
Right. And so you probably want to do things different ways.
Or include that it was corrected as a.
Right. So that should be apparent in the data, and so you could have utilized that. In what way might this make the accuracy of the data worse? And there's going to be conflicting things, but just in gross terms, how could this make the classification worse? Yes?
There's misclassification for all races, so this is the only race you could provide classification for that you're not fixing.
Yeah, I mean, the Hispanic white thing is the one that is probably the thinnest distinction. And in Texas, it's pretty common for there to be both European ancestry people and from South America ancestry people, but it's pretty, I think, apparent it would be in Texas. If someone is Asian, then you can, or black, mark them that way. But yeah, it could happen with other races as well, and a lot of stuff with this sort of race ethnicity thing. Census measures it in the way people of Caribbean descent or Puerto Rican or whatever identify themselves. Anyway, that's a whole nother thing, but it's a big deal in sort of science that basically the categories with which the census measures things are not necessarily the categories that people identify with. So they may identify with more than one. But there's a big one that I think the paper did not address. So how this could be worse.
It was previously said as first bit. I guess this the CMS using the code gets less wide than it should be.
That's certainly true. The one that jumped out to me was what if you have a woman of European ancestry who changes her name after marrying a Hispanic man. So just by looking at her, the police officer sort of legitimately recognized this person as white, but her driver's license says in that case, you would, I think, be pretty grossly misclassifying, even though the police officer probably got it right-ish. So
Yeah.
how prevalent is that?
Like, would it make it worse to like just do this technique with everyone? So like, I mean, just classify everyone. Don't take the data at all from the police officers, right? Like, only take the last name.
Only from the last name?
Because then, I mean, then you're consistently biased, I guess.
Yeah. With other, it's harder for some of the other races, but you still have the same thing of one, like the maiden name versus the married name thing for some women, and all sorts of other companies. So you could do it just off the name, possibly. But as to which one is better and worse, hard to think about. Well, it's easy to think about what the problems might be, harder to think about what the solutions might be. How would you estimate a negative binomial using BRMS? Didn't show what the code is, but it would be more or less like you would with our stand arm. You just call it the BRM function, family negative binomial, put in predictors and stuff like that. Have to choose a prior for phi. This is not the phi that shows up in the other parts of the paper. The rest of the model, the probability of carrying something illegal. This is the reciprocal over dispersion parameter. So again, negative binomial approaches a Poisson as this phi thing approaches infinity, and so you can use your beliefs as to whether you think there's going to be over dispersion, how much, etc., to inform your beliefs prior that you put on this parameter. But for a lot of things in the social sciences, there tends to be more dispersion than we would expect from a Poisson that has the expectation of the variance same. So last, write a function to draw from the prior predictive distribution. We don't have time to go through that right now. I might put it up tonight so you can compare your answer to what I got, but we've had plenty of practice drawing from the prior predictive distribution. This was just a slightly different form of the model where they were comparing, propensity to search, propensity to find anything in states like Colorado and Washington that legalized marijuana sometime during this period. And so there was basically no reason for those states to search cars or to arrest somebody for something that's no longer illegal. But then they did ask the question, well, even for states that continue to, for that to be a misdemeanor or whatever, does sort of, what's happening in, some of these other states make the police sort of less likely to search or less likely to care if someone is carrying drugs. So anyway, you can think about how you might draw from a prior predictive distribution of something. Okay, so I guess we'll end it on that note. But certainly if you have more questions, post them on Piazza. And I'll have office hours next Tuesday before the exam if there's anything that you want to talk about in person.